And here we are. This is the Physics 190 video lecture. Physics 190 video lecture 4. We're doing complex analysis. We were talking about the Cauchy-Riemann equations and an interesting application. So I'm going to repeat a bit of what we did, pursue that application a little bit further, and then move on into integration in the complex plane, which is really our major goal, but we really had to do this Cauchy-Riemann material as well. So any differentiable function, at all, a complex differentiable, f of z, has a real and an imaginary part, and so you can write them u of x and y plus I v of x and y, where u and v are real, right? There's the imaginary unit there. So any such function has these functions, real and imaginary parts u and v, that both satisfy Laplace's equation. With del squared u equals 0, del squared v is equal to 0. So yeah, Laplace's equation is an important equation of mathematical physics, and the applications are, the ones we've done so far are in fluid mechanics. It's even more common in electrostatics. But we did the fluid mechanical version for a reason, because we're going to run into that in 105B later in the semester. Possibly run into it, and it'll segue really nicely into this material. Okay, be that as it may, so we have these features here, and gradient u dotted into gradient v is equal to 0. This thing, which we didn't show in this form last time, but these two gradients are perpendicular to each other, which means that the equipotential, or the lines of constant u and the lines of constant v are perpendicular to each other. So the proof I did last time is a little bit involved compared to what we could do right here. Comma, all right, because du dx dv dy plus du dy. Oh, sorry, x. Right, I'm dot product of these two gradients, so you need x equals 0, and this, because the Cauchy-Riemann, du dx is equal to dv dy dx, and then du dy is minus dv dx. So yeah, this of course is 0, and I'll write here Cauchy-Riemann equations. So yeah, we have those conditions that we talked about last time. Now, because we were talking about velocity fields last time, I went ahead and used different letters. So we had f of z is equal to phi of x and y plus I c of x and y. That's what we did. Same thing. And I'll just write ideal fluid mechanics of 2 dimensions. The velocity field is equal to the gradient phi of x and y. And x and y equals constant, which you can say equals 0, gives the streamlines at the boundary. At a solid boundary. So this was for fluid mechanics. And then what did we have? We had, as two examples, f of z is equal to z to the n. We had n equals 1 and 2. And I'll just do the n equals 2 version. X, y. So we had z squared is equal to x squared minus y squared plus I times 2xy. I had a constant in front of there for dimensional reasons, but we can drop that for now. Just look at the pure numbers here. And then we had this function, right? So this was phi of x and y, and this was c of x and y. So this function took on the value 0 at x equals 0 and y equals 0. So we're in the first quadrant, and then these streamlines are like this, and this actually, if you take the gradient of this function here, those values are parallel to these streamlines, and so that's actually the ideal fluid flow in a corner. Okay. So I had talked about going to higher powers here, and that's where I'm going to pick up right now and just extend this discussion a little bit. So we'll pursue this problem. So next, f of z equals z cubed. And as a complex function, this is so simple, but it's x plus I times y cubed. And this one we could just still multiply out. Anything more than that's going to get very tedious. Okay, so what can we do? Plus iy cubed, and so cubed to the 4th to the 5th, you're going to get more and more complicated expressions here, and you're not easily going to see what we saw here for this first quadrant corner, right? X equals y, x equals 0, y equals 0, gives us 0. So there's a way to convert the Cauchy-Riemann equations to plane polar coordinates that we don't want to do now. Okay, that's a whole other set of problems. And we're not going to have to do that. We can get the insight that we're looking for these higher powers. I'll just put a note here just so you have it for the record. F of z equals z to the n. X plus iy to the n, right? If n's greater than 3, even 2, it's starting to become tedious. So I'll just put here difficult to evaluate, and evaluate what it means, even though, looked at right here, this is a very simple function. So what we're going to do is consider the third power, f of z equals z cubed, and we'll go into Euler's form here. So that's r e to the I theta cubed. And now this is r cubed e to the I times 3 theta. And continue right here. So we have r cubed cosine of 3 theta plus I times r cubed sine of 3 theta. Okay, now we want to discuss this in the xy plane, and we have the wrong coordinates here. We can't just take derivatives of this anymore, right? Our gradients are in x and y. But we can still get some important information out of this. I'm going to send this up. We can get the crucial information that we're looking for. Namely, what does this problem represent? What does this represent in the plane? So the thing that we have to take note of, we're looking for, so we have u of x and y plus I, wait a minute, I'm using phi and c. Okay, so phi of x and y plus I times c of x and y. On the one hand, if we take what we have here, you see we have r cubed cos 3 theta plus I times r cubed sine of 3 theta. And what we wanted to find is, where is this function equal to 0? Because that'll be the streamline at the solid boundary. And we can see where this is 0. So this equals 0 when theta equals 0 and 3 theta equals pi. Okay. Or theta equals pi over 3. Okay, that's very well defined. So you're in plane polar coordinates. Let's draw our picture here. This is the xy plane, complex plane, but pi over 3, that's your 60 degrees. So roughly there. So this is the new boundary of that function. Okay. The function z to the n equals 1 power had the first quadrant. Okay. And the xy axis is the boundaries. Here it's the x-axis theta equals 0, and then this ray right here, theta equals pi over 3. And constant values of this, so I also r cubed sine 3 theta equals constant, without actual proof of this, but yeah, those are curves that go like this. So your streamlines are like that. And if you think about it, you can see how that's going to work, because this sine of 3 theta, when theta equals 0, it's always going to go tend towards 0. And when theta equals pi over 3. But if you're off of that 0 value of the constant, the next constant will be r to the 3rd. That will be your constant. So r would be the distance, say, from here to here. That to the 3rd power is your constant. And then this function never actually vanishes, because the angle never strictly goes to 0, never strictly goes to pi over 3. In the limit out towards infinity, it gets very close. Good. So yeah, that's the fluid flow in that case. And now you can see what would be the situation for r to the n. f of z equals z to the n, you would have r to the n e to the I n theta. And you do the same thing I just did, and you see for each higher power of n, you'd have a smaller and smaller wedge, okay, in which the fluid flows. Okay, so that's for fluid flows. Let's see if I have anything else to say there. And what's amazing is just any function that's differentiable is going to be the solution to some problem. It may not be that easy to find out what problem it solves. Right? This is a really formal method here. But for some, you can find it, and it turns out to be the lower powers. I'm going to end this section by talking about electrostatics as well. Not to pursue the electrostatic problems, but to make sure you recognize that the method is applicable. So let's just call this complex functions and electrostatics. This is actually the part of the theory that would have occurred to you before, because we tend to do more electricity and magnetism than fluid mechanics. Good, so complex functions and electrostatics. Let's go back to f of z equals u of x and y plus I v of x and y. And f of z is differentiable. Okay, f of z is differentiable. Now, immediately we have del squared u equals 0. Del squared v equals 0 in the two-dimensional case. So that's what we had before. In electrostatics, what do we have? We have the electric field being equal to minus the gradient of a potential. Electric potential and if we're in a region with no charge, then divergence of E is equal to 0. You see, the fluid and the electrical cases are very analogous. In fact, as we'll discuss later when we're in 105B, the electrical formalism was discovered after the fluid formalism, but in electricity it happens to work much, much better than it does in fluids. But that's a discussion for later. So yeah, we have divergence of E equals 0 in a region with no charge. Think of Gauss's law. And therefore, we have del squared of V is equal to 0. Divergence of the gradient of the potential is equal to 0. So everything we said about the fluid case is true here in the electrical case as well. You get the Cauchy-Riemann equations. You have both of these potentially being potential functions. And again, you can take very simple functions, tease them apart like this, expand them, and then you have to look for what electrical problem do they actually solve. So that's probably as much as we're going to do here. It's definitely important to recognize. Actually, you know, we could do the simplest version of this just to make sure. And it also brings up the point that in fluids, we've made this velocity potential and this the streamline function. But you can actually reverse the meanings of these because they both satisfy del squared equals 0, right? They both satisfy Laplace's equation. So I'll do an example. I'll do the simplest example just so we see the electrical version of this. Example. And I'm just going to do f of z equals x plus I times y. So right under here, I'll say this u of x and y is equal to x. This v of x and y is equal to y. So if you took constant values of y, then you could call this your potential function. So let v be the potential function. Now, constant values, how about another color here? Constant values of y are like this. Okay. So your equipotentials are like that. Okay, just as constant values of y. And now gradient of v is equal to 0, 1. Okay, so your field vectors, your field is like that. And plus or minus depending upon the way the constant values go here. So I'm not going to worry about the sign right now. It's just the fact for perpendicular, you've got constant. Make this the charge plate, constant values of v. In fact, the numbers should work out as well if we had a increasing potential, then minus gradient like that. So if potential is increasing in y direction, then negative the gradient reverses the arrows. Good. That's as far as we're going to go. So Cauchy, Riemann, and Laplace's equation, a whole world of excellent applications. The ones we actually wanted to pursue are in a different direction, but you really have to make a detour here, and we did. So, like I said, we'll be able to make contact with this conceivably towards the end of the semester. If we're doing fluids, we'll segue right into here and discuss the fluid version of this once again. Okay, the next section is to discuss integration in the complex plane. And I'm just going to get the subject started this time, and then we'll prove some theorems in the next lecture. Let's see how we're doing. This isn't going to be a long one. Okay, time flies. Okay, so let's just call this, how am I going to title this section here? Yes, Cauchy integral theorem. So we're working our way up to the major theorem in complex analysis. Won't take that long to get there, from which everything follows. So Cauchy integral theorem. So first we have to discuss what is integration in the complex plane. So we're in the complex plane here. I'll just say it's the complex plane. And we're going to do integrations along a contour, say from z sub a to z sub b. And we have to define an integral f of z dz along the contour c. And this is really straightforward. Okay. What we do is, first we divide the contour up and do a bunch of individual points along it. Okay. And then we construct the sum S sub n, and we're going to sum f of z sub I times z sub I plus 1 minus z sub I. So this is just like a Riemann sum. And what's interesting is because of the vector property of the complex numbers in the complex plane, this difference acts or is just like a short vector. Okay? It's like a little directed segment, because if there's your ith and your I plus 1 point, then your delta or your delta z is really that directed segment, and you're multiplying it by the value of the function at one point. Okay? And if you're summing those up, you're going to write I equals 1 to n, and this of course corresponds with the point A, and this corresponds to the point B. So that's a very straightforward definition, and to turn that into an integral, we just have to have the ever finer subdivision along the curve, along the contour. So in the limit as n goes to infinity, this will turn into this integral here. So then limit n goes to infinity at this s of n is going to be equal to that integral. So along the contour, f of z dz, that's exactly how this is defined. And in that limit, the point at which you evaluate f of z is of course immaterial, because these things all become infinitesimal. And we can also say, if we're out here at the endpoint z sub b, we can say this integral defines a function of the endpoint. And because this is just constructed with the normal algebraic properties of real and complex numbers, the derivative, this f prime of z sub b, would be the value of the function in the integrand at z sub b, just as you have with the ordinary fundamental theorem. Okay, so this is a fine thing indeed. So now we have the definition of an integral, and in terms of your basic functions, you just take antiderivatives, so most of your integration rules hold true here as well. There can be some really interesting twists to come along, but you know, if you had z to the n, then the antiderivative would be, you know, z to the n plus 1 divided by n plus 1, and so forth. So yeah, let me just write that down as an example. Evaluated at that point. Okay, I'm just actually going to leave that there. That's a very clear definition of how an integral comes together. Okay? And the actual properties of this we're going to learn as we go along. You know, the interesting properties. If you were just living along the real axis, it would just be everything you know about integration. That would be a standard definition for an integral. Okay, so we're going to do one little theorem today and then call it good. It's called the Darboux inequality. put here triangle inequality. You'll see in a moment why. So the Darboux inequality is a way of getting estimates for certain integrals. So what we do is, in fact, I'll just do the construction. So we have the sum. What we'll do is we'll start with S of n there. So we'll have the sum of f sub zi plus 1 minus z sub I. Okay. We're looking at that and we want to estimate it as to its magnitude. And of course, this is our, I'll write S of n here. Okay. So say we want to find the magnitude of this. Then we know from the triangle inequality in general, we go inside the sum, we have an inequality, so f of z sub I plus 1 minus z sub I. And we can estimate this again, sum of f sub z sub I magnitude of z sub I plus 1 minus z sub I. And now, this again will be less than equal to the maximum. Let's just say we're doing this is on a curve, on a contour, I'll just put C there. So this is less than equal to the maximum magnitude f of z along that contour times the sum over these z sub I plus 1 minus z sub I. But what is this here? But here I'll use blue. In the limit, this is of course just the length of the curve. So I'm just going to put here in the limit as n goes to infinity, what we have here is f of z maximum on the curve times the length of the curve C. So yeah, the Darboux inequality can then be formulated like this. The integral f of z dz along the curve can be estimated as less than or equal to f of z's maximum magnitude on the curve times the length of the curve. So there's your Darboux inequality. And there's actually a stronger inequality than this one that we'll use later, but this is a good one to get started with. So we'll do an example of it. And this example, interestingly, takes us right into the heart of the subject. So here's our example. Let's look at the integral 1 over z squared dz along this, I'm going to call it contour sub r. And what is that? Let's go ahead and call this point A and this point B. This is the complex plane. Okay, so we're doing an integral from A to B, and it's this semicircle of radius r. So the semicircle of radius r, and what we want to do is get an estimate for this thing. This is one of the crucial integrals of the whole semester. Okay, so what do we have here? Well, let z equal r e to the I theta. R e to the I theta, and we see that we're going to have 0 less than or equal to theta less than or equal to pi. Okay. So that will actually transform onto our contour there. So this integral would transform into 1 over z squared, so 1 over r e to the I theta squared, and then the dz is just going to be I r e to the I theta d theta, right? dz d theta is I r e to the I theta. Okay, so there's our dz. So we have I r e to the I theta d theta. Okay, but we just want to estimate this thing. We're not going to calculate this one right now, but rather do an estimate in the sense of the Darboux inequality. So what we'll do is estimate this thing. I think I have enough room. Integral 1 over z squared dz along this c sub r here. And we know that is less than or equal to integral 1 over z squared dz, right? The magnitude of both of those. And in fact, well, I'll write it extra. So integral 1 over z magnitude squared. That's the same thing. dz magnitude. So now what do we have here? 1 over z magnitude is just 1 over r, right? When you do a complex conjugate magnitude and square it, it's e to the I theta times e to the minus I theta is just 1. Okay. I want to write that down separately. That's so important. So what we end up with is 1 over r squared, and then we're integrating from 0 to pi. We've got d theta, and the magnitude of this, again, the I magnitude is 1, the magnitude of e to the I theta is 1, so it's just r. So what is this? R over r squared is 1 over r, and then 0 to pi is pi. So we end up with equals here in the right-hand corner, where it always ends up. We just end up with pi divided by r. And so I'll just put as an important note here, in the limit as r goes to infinity, this integral vanishes, right? As r goes to infinity power. So very important note. Limit r goes to infinity, pi over r is equal to 0. Okay, very important, because we'll be doing quite a bit of this later on. We often do integrals from minus infinity to infinity on the real axis, and if we're able to extend them into the complex plane, then the entire contribution from this semicircle is very often 0. In fact, we want it to be 0 more often than not. So that's going to play a big role, and we'll get more powerful estimates, but the Darboux inequality is very transparent. It's the first one. I put that as this other note that I was mentioning. So z complex conjugate squared, that's r e to the I theta times r e to the minus I theta. Right, so that gives you the 1, and that's where that r squared comes from. Down here, it's the 1 over r squared. Okay, yeah, so this is an example of what we're going to be doing a lot of. Integrating around the complex plane along paths, these semicircles are just the path of choice in many cases. And like I said before, the definition of the integral is just so straightforward that you should feel really comfortable with this. And also the transformation to a contour is really exemplified by what I just did right here, okay? So these basic contours are very straightforward. And other ones, we just wave our hands around and indicate contours in the plane. This is a concrete example, very easy to do. So we'll call it good right here is the end of this lecture. And what we'll do next time is Cauchy's integral theorem, where we have to use these techniques. Okay, good. See you next time.